Okay, so the last part of this video, this week's lecture is about visual motion perception and the middle temporal area. Sometimes it's called MT, sometimes V5, depending on where you are. In US, it tends to be called MT, and in UK, it's called tends to be called V5. So the V1, V2, V3, that's what we already covered. And then MT or V5 locates slightly anterior or temporal to the visual cortex, like this way. And this area tends to contain lots of neurons that respond to the visual motion. And just one word of caution. We talk about MTL in the at least in the next lecture, and it is a medial temporal lobe. Okay, medial means the inside compared to lateral, and the temporal means this temporal lobe. And middle temporal lobe MT is the sort of the middle of the temporal lobe. So that's a different medial temporal versus middle temporal. Okay, and the medial temporal lobe contains structures such as the hippocampus and amygdala. That's are important for memory or emotion. So don't confuse MT and MTL. Okay, so let's go to MT. Before getting to the MT, I first want to show another video, which is about the motion after effects and its relation to consciousness. Okay, and again, we go to this Michael Bach's website, and this one is about rotation motion. So here, I want you to fixate on the center part of the video, and then do not move your eyes. Okay, this blue red part. And if you are like me, and then you can do it again. Don't move your eyes and don't blink. Adapt, adapt, adapt. And then after a while, you see this, yeah, so this Buddha thing, which is located probably in Kamakura in Japan, that should appear expanding to you. And then again, once again, just in case you don't see it. Yeah, and yeah, it expanded. So this motion after effects, like other after effects, orientation after effects or after image, it accumulates over the time. So the more you do it, you start to see the expansion much stronger. So the next time the expansion should be much stronger. Yeah, I feel like radiation kind of line coming out from the Buddha as well. Okay, so that's the motion after effect. In this case, it's a radial motion after effects. Okay. So we can do the same kind of experiment as the crowded version or illusory contour version for this experiment. That's what people have done. This is a paper by my previous postdoc, Lisandro Kaunet. He did it not with me, but published in 2011. So the point of this paper was that the adaptation to the visible versus invisible motion was compared as a function of the motion's complexity, simple version versus complex version. The first experiment, what he did was to present some kind of grating to the non-dominant eye. Most likely, many people have non-dominant eye on the left eye. And then to the dominant eye, he presented some kind of flickering pattern called the continuous flash suppression, which I'll explain in later weeks. And that's something that I discovered when I was a PhD. So here, what he did was to present either this grating that moves either only upward or downward, and then for roughly 1 minute, and then presented another stimulus right after that. And then after that, as I said, this kind of motion after effects accumulates, but once it accumulates, it stays on. So 2 seconds of the top up adaptation and then test, top up, test, top up, test, top up, test kind of thing. So under the visible condition, you don't show any kind of continuous suppression, and then just adapt to this motion for unidirection. If it's up condition, up, up, up for 1 minute, and then test, and then visibility for upward or downward, and then go to the 2 seconds of the up, and then up or down kind of thing. And he tested it with both eyes, adapted eye or non-adapted eye, like this way. And he crossed it with visibility suppression. So if he didn't show anything like this, then this one becomes visible. But if she showed the continuous suppression, he was able to suppress the stimulus quite effectively. Okay, so that's the first important condition. And then next, what Lisandro did was to present complex motion. So here it looks like sort of the expanding or contracting motion for the Buddha demo that I showed, but he used a spiral motion. And the spiral is believed to be processed in 1 step higher than the MT. It's called the MST, middle superior temporal sulcus. Okay, temporal lobe or something like that. And then here, this next stage of the MT, it processes a radial motion or spiral motion. And he made again visible or invisible kind of condition, and the test was whether the contraction or expansion of the spiral was perceived. And then importantly, what he did also was that he added another attentional condition. So importantly, what he added was this attentional condition. So on the dominant eye, suppressive stimulus was presented. He presented some kind of letters similar to the attentional manipulation in the previous study. There, people were either attending to these letters or not. And then he asked the question of whether attention or conscious visibility is necessary to get the motion after effect. So here is the result of his finding for the simple motion. So in the case of the simple motion, when the stimulus was visible, so this is visible, and then this black one is invisible. No attention task or easy attention task or difficult attention task. So it's a 2x3 design. As long as stimulus was visible, no matter what attention was withdrawn, stimulus was processed, and the motion after effect was very strong. And there is some kind of relation as a function of the strength of the attentional distraction. But importantly, invisible stimulus still produced lots of after effects, and it's strongly above chance. Above chance performance is defined above 0.5 here. Okay. And then the complex motion. So in the case of the spiral motion, when he did it with a scene adapter, no suppression, then the adaptation was very strong, and regardless of the attention. But if it's invisible stimulus, then even the attention task was very weak. It already became at chance level, and this one as well. So the visible and the complex motion evokes motion after effects, but invisible complex motion evokes very weak motion after effects, if anything. And this kind of psychophysics experiment has been also combined or backed up by the fMRI experiment in humans. So here, it was one of the first studies on this kind by Roger Tutel in Massachusetts. What he did was first to locate the area MT in this, inflated brain, or it's embedded sometimes in subjects from the right visual field, and then he asked people to, adapt to this expanding motion for roughly 40 seconds or so. Okay, 40 seconds, or contraction or expansion. And then after that, he put the stimulus on for 40 seconds again, and then looked at, invoked the motion after effects from the subjects. So here, 40 seconds of expansion, and then 40 seconds of the static, and then expansion or contraction, and then static, contraction, static, expansion or contraction, and then static. So that's the sort of the design of the experiment. And each of the block is 40 seconds. And then this is an fMRI response at the, this MT area. Okay, so MT area's response was like, at the beginning, it was baseline, and then it increases and then goes down, but with substantial sort of, residual activity here. And that's what Tutel analyzed further on, combining with the psychophysics. So what they found was that aligning across all these, trials, they found that at the end of the motion, when the stimulus was presented, then stationary stimulus was presented, then there is strong effects of transient, increase in fMRI in the MT areas. Okay, and that invokes this stimulus, and this one is already subtracting this motion component already. And then the important thing is this, quantification of the psychophysical motion after effects at different time point. They quantified how strong the people were experiencing the motion after effects. And then what they found was that this motion after effects decay, and that's something that you probably also feel if you test this, Buddha, motion after effects thing by yourself. After the time, it starts to stop. So this is a very nice correlate it's quite a tight correlate, I should say, between the motion after effect or perception of the visual motion, quality of the visual motion, and neuronal activity. And importantly, this type of the correlation should be also compared with the causal evidence. And in terms of the human, most straightforward causal evidence comes from the patients. And here, the patients receive undergone MT, bilateral MT lesion, reported this condition called Kinematogram. And this is a specific deficit in the perception of the visual motion, but nothing else, due to the cortical lesion in and around the MT area. And this type of the phenomena has been reported in the monkey, like, blind side case. Physiologist has made lesion in monkey, and then characterized the performance, which looked similar to these MT patients, basically. And this video is fiction, but I find it very compelling. So let's watch about that and then see.
78, a 43-year-old woman was admitted to a hospital in a stupor. She had suffered for 3 days with severe headaches and vomiting. Several tests run then and later suggested that a stroke had damaged both sides of her brain at the lateral border between the temporal and occipital lobes, here indicated by a dark spot. 19 months later, in May 1980, she was examined by neurologist Joseph Zill, and in most respects was found to be normal. She could read, write, and calculate. She had no trouble moving her body. But, as Zill reported in 1983, she had an unusual complaint.
The visual disorder complained of by the patient was a loss of movement vision in all three dimensions. She had difficulty, for example, in pouring tea or coffee into a cup because the fluid appeared to be frozen like a glacier. In addition, she could not stop pouring at the right time since she was unable to perceive the movement in the cup when the fluid rose. Furthermore, the patient complained of difficulties in following a dialogue because she could not see the movements of the face and especially the mouth of the speaker. In a room where more than two other people were walking, she felt insecure and unwell and usually left the room immediately because
People were suddenly here or there, but I did not see them moving.
So
she could not cross the street.
so that's probably enough to get some kind of intuition about what the patient would have experienced.
Okay, so that was a fiction, but it looks kind of comparing description of the empty lesion patient. Sometimes it is described as a strobe-like situation, but it's a very rare lesion, so we don't know much about this type of the patients. It needs to be studied further. All right, so then in terms of the columnar organization, I mentioned it briefly last week, but MT contains neurons with the columnar organization across the direction and also depth of the motion as well. And this means that it's actually useful for us to think about the sort of the micro-stimulation experiment that I'm going to talk about in next slides, because electrical currents that is passed in a local neighborhood of the neurons, which prefers that vertical orientation, vertical direction of motion or something like that, then many neurons that prefer these direction can be effectively stimulated by local stimulation. But before going into the microstimulation, I need to talk about this very famous paradigm of the MT neuron and psychophysics. So this is the stimulus called random dot kinematogram, pioneered by this motion physiologist Kenneth Britton and also Michael Shadran and also Bill Newsom. As you can see, so this the degree of the coherence or correlation of the motion can be parametrically manipulated like this way. So 100% correlation motion means that all the dot moves in the same direction, and no correlation means that from one frame to the next, all the dots are redrawn completely in a different location. So it looks really a random motion. And 50% correlation means that 50% of the dots are drawn in the random location. So how it looks like. Okay, so here's the example of the random dot motion stimulus. So what if you stop the frame, you will see that bunch of dots, and then initially it's moving in a completely random, redrawn in a different direction, location, and so you presumably didn't have a comparing, motion direction. But if most of the new dots move to the left, then everybody see the motion to the left. Okay, so nice thing about this dot motion stimulus is that you can change the number of the dot moves into particular direction and also the other direction in a parametric manner. So this groundbreaking study conducted by Bill Newsom and colleagues basically showed this motion to the location of the receptive field of the neurons in MT. And then they presented different level of the coherence motion to the monkey. okay, at the location. And then they also ask the monkey, train the monkey for months and so on, and then let them report which way the motion was moving. In this case, let's say upwards or downwards. Okay, and then when the motion stimulus contained quite a bit of the strong correlation, let's say 12% or so, then one single empty neuron may fire a lot, let's say up to 100 hertz, 100 spikes per trial. Okay, spikes. They counted the number of the spikes. And here, so this is a 12.8% trial, and then some of the trials produced this neuron fired a lot. On the other hand, if it's let's say in this case it's upward motion, and this is a downward motion, then this neuron didn't like this downward motion. So sometimes, most of the cases, they fired much less. And then there is a mean peak here, and then here peak as well. And you can imagine that we can do the signal detection type analysis by putting the criterion here and then compute the area under the curve. And that's what they did, in fact. And then they generated a different level of the coherence, and this 0.8 is almost invisible to make upper or lower type discrimination. And as the coherence goes down, correlation goes down, neuron gets confused. That's the upshot of this figure. Okay, and then what was interesting is that when they look at the monkey's performance, which is this white dots, this is monkey's report. So remember that during all these experiments, monkey was also reporting this percent, and then they plotted the proportion of the correct as a function of the correlation. Okay, the stronger the stimulus, the monkey became much accurate. Okay. And then this is one particular exemplar MT neuron. So performance by coming from this, they put the criterion here and then said, okay, so this one corresponds to, let's say, 80% correct. So it would put something like here, or maybe because it's a 12%, it corresponds to something like this, almost 100% accuracy. And then if it's a correlation of 0.8 here, then it's almost indistinguishable, so it corresponds to here, and so on. Then they found that on average, they could always find a neuron that responds at least slightly better than monkey. And MT is a bit farther away from the motor cortex, which controls the monkey's report. They thought that there is some kind of noise coming in and degrades this purely motion information down the way to eventually will result into monkey's report. So far it's it's a great study, but not super relevant for consciousness per se. But a further experiment by Zlatzman did more relevant experiment. So here the monkey was fixating at this location, and then they made a decision between this direction of motion and this direction of motion for one particular MT neuron. And then monkey was reporting the direction of motion by the eye position. If it's moving this way, then they move the eye here. Then if it's moving this way, then move the eye here, something like that. And then not only the visual stimulus was presented between T2 to T3, they also delivered the electrical stimulation around the neuron that they recorded after the recording of the neurons. Okay, and then they found that as a function of the correlation, without the stimulation, okay, monkey reported something like this way, and then proportion of the preferred decisions for this particular location. And this is at 0. So, at the 0, then monkey tend to say 50-50 in this case, and then there was some kind of bias to say, oh, I say to the bottom or something like that for this particular experimental session. But the important thing is that when they deliver the electrical stimulation, microstimulation, then the monkey's report, conscious report, became more biased towards the preferred direction. So the stimulation increased the proportion of the report by roughly 10% to 20%. But that corresponds to, so this is actually quite significant because here the electrical stimulation skipped all the way from the retina to LGN to V1 and then directly stimulated MT. And this artificial stimulation was, in a sense, confused or perceived by the monkey, almost like a motion stimulus. And then that's why they reported like this. Okay, so this motion electrical stimulation experiment is very important in terms of the building this causality between the MT neurons activation and motion perception. So in summary, MT's causal role for the visual motion qualia is strongly implicated by the phenomenology and psychophysics and the FMRI and the lesion and the neurophysiology and microstimulation. It's very compelling. And bilateral lesion abolishes motion qualia. This is very important. And also microstimulation causally interfere with the motion. So these two things are one of the most compelling evidence. Now, important question for the consciousness researcher is why does MT generate motion qualia? And at this point, really nobody knows. And you need to think about what is special about MT. Okay? And some may say that it is an input, or some say maybe it's the output. It is directly related to the behavior or sort of the verbal report of seeing motion. But that doesn't make much sense. If you don't report anything, but you can still see the motion. And in terms of input side, if it's a input, let's say retina to MT in a certain configuration generates this pattern of the input, and that defines MT's role of visual processing and then generate qualia. Why this input actually needs to cause this motion qualia? That's the question. Another possible answer would be there may be something really specific about MT's neurons biophysics. Maybe some special receptor that generates motion sensation, which we can't really rule out at this point. And also another likely scenario that at least what I think is that in local neurocircuitry, which is related to all these layer structures and also neuron excitatory and inhibitory population, and also columnar organization, all of these are potentially related to the key to the explanation of why MT generates motion qualia. And this is exactly the hard problem. And if you can figure this out, it's potentially like a Nobel laureate prize. It's really unclear at the moment. And the philosophers and neuroscientists are all at a loss. And then so that's another form of the hard problem. So that's another form of the hard problem, which we will further discuss and also look at by looking at other areas of the brain as well. Okay, see you next week.